Okay, so in previous lecture, we discussed about how the LiDAR concept of LiDAR evolved. Okay, and there we discussed about this how the total station work. So we discussed that total station is a combination of electronic distance measurement instrument and theodolite. Okay, then we talk about limitation of TS based data acquisition, and then we derived why the concept of why the LiDAR technology like LiDAR is required. Okay. So we discussed till the basic concept of LiDAR, like how the laser is generated and how we can define a laser pulse. Okay. So further we discuss about this when you initiate a LiDAR instrument. Okay. Then if you see in figure A, so after initialization of LiDAR instrument, laser beams are fired. So the laser beams, we have two types. The first one is the pulse laser. Okay, as you have seen over here. So actually in ideal, in practical case, we can't generate actual exact square pulse. So it is Gaussian in nature, as it is already discussed previously. So this will be a shape of one particular laser pulse. Okay. So series of laser pulses are generated at a particular rate. So this is one type of laser beam. And the second type is continuous wave laser. So either in the form of sinusoid or cosinusoid, the laser beam is generated. So if you see the difference between the pulse laser and continuous wave laser is that in case of pulse laser, energy is confined only within a certain this time difference. Okay, and we call it this pulse width. So energy is only confined within this pulse. Then there is a gap. Okay, and after that, again the same pulse is transmitted by the transmitter. Then again there is a gap. The next pulse is transmitted. While in case of continuous wave laser, continuously energy is transmitted, okay, in the form of laser beam. So we'll see later on, we'll see the differences between these two. Okay, like in the existing LiDAR system, the which particular laser pulse is selected for the operation. Okay, whether it is pulse laser or continuous wave laser. Okay, what are the advantages, what are the disadvantages between these two types of laser pulses? Okay. For the simplicity, in this case, I have considered the pulse laser to understand the basic operation of LiDAR. Okay. So is there any query related to this discussion? Okay. So in this case, we have already discussed like when a pulse is generated, okay, then it goes to towards the target, and it is strike to the target and return back. So total time of travel is recorded. Then the range is calculated, and this range is equal to c into time of flight divided by 2. Okay. How we can calculate the coordinate of a particular point? Let's say if the point is located at position 1. Okay. So when the laser beam is transmitted, and the nature of laser beam in this case we have considered the pulse laser. So a particular pulse is transmitted, and it goes along this direction, hit the point at target 1 and return back. Okay, so this range is calculated internally. Okay, what additional parameters are required to calculate the coordinate of point 1? We have already discussed previously in the context of total station based operation. Shivam, could you please unmute?
Yes, sir.
What is the query that I ask?
Sir, what's the principle for distance meter?
What?
Sir, what's the principle for the distance meter? Like ADM.
No, this was not the query. This was not discussion that I have been doing. Are you listening carefully?
Yes, sir.
Then what I discussed? See, I have been discussing about operation of a LiDAR system in the context of figure A, where a laser scanner unit is mounted on the tripod. Okay, so tripod is a static platform. On top of it, a laser scanner unit is mounted. Okay, and it is continuously generating the laser pulse. Okay, and these laser pulse are hitting the points at a different locations. And let's say if one laser pulse is fired, then there is a change in orientation of a laser scanner unit so that next pulse hit the point adjacent to the previous one. Okay, so when this at let's say at time t1, if we consider at this first laser pulse is fired at time t1, it is recorded. Okay, it goes towards target 1 in a straight line, return back. So how we can calculate the range? Yeah, Shivam, please.
Sir, actually sir network break हो रहे हैं sir बार बार.
Now it is clear. Can you see the shared screen?
Yes, sir.
If you can see the shared screen, then the query is straightforward. How to calculate the range? What is the process?
सर पल्स स्ट्राइक होता है सर ऑब्जेक्ट जिस जो सर मतलब जो आपकी सर लेजर मशीन है वो ट्राइपॉड पे माउंट की जाती है सर. उसके बाद पल्स स्ट्राइक होती है ऑब्जेक्ट पे. और जैसे सर पल्स ऑब्जेक्ट पे स्ट्राइक होती है उसके सर फर्स्ट पल्स जिस पे स्ट्राइक होती है नेक्स्ट टाइम उसके एडजेसेंट साइड्स पे सेकंड पल्स स्ट्राइक करती है सर.
नहीं, चलो गुड. So now query the problem is further extended. It is fine. Like due to change in orientation of this unit, what happens? There is an internal rotating mechanism that I will discuss in the coming slides. When you initialize this instrument, so what happens when the first laser pulse, let's say it is fired at time t1. Okay. Now the next laser pulse that is fired at time t2. Okay. Now at the time t2, the orientation of the laser source, you can say, the orientation of transmitter different. Let's say now it is hitting the second point. Okay. So at time t1, the laser pulse strikes at point 1, while at time t2, laser pulse strikes to the second point t2, that is 2 at time t2. Now the query is related to the information acquisition of the first point. So what kind of information is acquired by TLS, this LiDAR instrument? Who will tell me? Through this entire process, what kind of information from point 1 is acquired?
Sir, distance of point 1.
Okay, distance of point 1 from where?
Sir, from the laser source.
Correct. So see, if you see in the figure B, a block, this particular block indicate the laser scanner unit. Okay, so from the there is a transmitter. That transmitter has a laser source. It fires the laser pulse. Okay, so from the laser source to the target, let's say this is at location 1. This is point P1. Okay, so laser pulse goes along this direction in the straight line. Okay, they hit the point P1, return back. So in the process, what is the raw information that is calculated and how the range is estimated?
Sir, time is calculated. How much time it takes?
Sumit, please mute. I will ask someone else. Arun Kumar, could you please unmute? Arun, are you there? Can someone call him? That he is being asked to respond. Okay. By the meantime, Praveen, could you please unmute?
Yes, sir.
Yeah. So how range is calculated in this case?
Hello, sir. It's Arun.
Yeah, I will call you later. Yeah, Praveen.
Yes, sir.
Yes, tell me. How the range is calculated in this case?
सर रेंज नहीं पता है.
So what you have understood in the discussion that we had previously and now we have been doing? What is the range here?
एक्चुअली सर आज हमारा फर्स्ट लेक्चर है.
Okay, fine. So be continuous in the class. Okay, don't skip the classes. Yeah, Arun.
सॉरी सर, मैं नेटवर्क इशू था इसलिए मैं फिर से रिज्वाइन हुआ हूँ सर.
That is fine. That is fine. No issue. Just tell me how the range is calculated over here.
Sir, simply as a distance one, sir, because we have a 2 point from LiDAR, the instrument, to the point we projected. So we just measure the range from that distance one.
Okay, see, all of you, please carefully listen. You have already done the experiment based on total station, okay? And as I discussed before, total station is comprised of, it's an integrated unit where we have EDMI and theodolite, okay? And I hope you are aware about this conversion, where by using total station, what we do, we calculate range from the source to target. Okay, and we calculate two angles, one from the vertical, that is alpha, while another one from the reference horizontal axis, whether it is y or x. Okay, the same concept of total station we apply in LiDAR. Okay, where inside the laser scanner unit we have the angle encoders. We'll see it in detail when we discuss the internal architecture of laser scanner unit. But for general understanding, just like total station, in the LiDAR, when you initialize the instrument, what happens? The EDMI, electronic distance measurement instrument, the EDMI electronic component that is part of TS, this TLS, our LiDAR system. There is an internal laser source. That laser source generates laser beam. In this case, the laser beam I am considering the pulse laser. Okay, so we have two types, pulse laser and continuous wave laser. Fine. So for this problem statement, for the general understanding, I have considered the pulse laser over here. So at time t1, okay, a laser beam is generated that is pulsating in nature. It goes in the medium, hit the target and return back. Okay, so this medium is air over here. So in air, the speed of laser beam is considered as speed of light c. So we know at what speed this laser beam is traveling in the medium, that is known. Then internal electronics, that is a particular component of laser scanner unit where the time is recorded. So there is a counter circuit that is an internal component. It records the total time of travel, that is time, we call it time of flight. So this time of flight t is the time taken by laser pulse from laser source to point P1, that is target, and further the return back to the source. So this beam travels in a straight line. Simply the range is calculated by multiplying the half of this time into c. Now I hope it is clear to all of you. All of you raise your hand. There is option to raise your hand. Praveen.
Yes, sir.
It is clear to you?
Yes, sir.
Okay, good. Okay. So just see the raw measurements which are recorded, they are range. Then there are angle encoders. So alpha and beta, these two angles are also recorded. So for that particular laser beam, let's say if we consider it for target point 1, okay, the R alpha and beta is recorded. And in a Cartesian coordinate system, we can calculate the location of this point 1. Okay, that is x1, y1, and z1. So you can have a kind of three-dimensional analysis. Okay, in Cartesian coordinate system, like in this case, this x, y, z coordinate system, it is in Cartesian coordinate. So point P1, its projection on x, y, and z axis. Okay, that gives the location of point P1 is calculated. That is x1, y1, and z1 by using this formula. Okay. Now, what is the benefit of LiDAR over TS? Because see, let's say for this particular problem statement where our aim is to do the geometrical surface generation of this terrain. If you want to geometrically represent this terrain, how it can be done? It can be done by computing the coordinates of these closely spaced points. Okay, we can say them like they are near uniform distribution. So these, when you have a points coordinates, if they are given, so you can able to generate a mathematical surface by using this coordinate in 3D. Okay, and that gives you idea about this terrain. If you want to perform the same task, using total session, then what you need to do for each point coordinate measurement, you need to initialize your instrument. It is not automatic. Okay. You need to have a kind of reflector over there at a target point. You need to set. So the two persons are required. The one person should operate the TS while other person should hold the this mirror. That is a target mirror. Okay. But in case of this laser scanner based coordinate acquisition of these large number of points, just you need to initialize the instrument. It automatically fires many laser pulses. Okay. Once you start, it starts firing the laser pulses at a certain rate. Okay. And provide them a different direction so that all these points are captured. Okay. So for each point, this alpha, R alpha and beta, they are computed. Okay. And finally, we calculate the location of point in a Cartesian coordinate system in terms of x1, y1, and z1 projection of on three different axes. So this is a basic fundamental through which the LiDAR technique work. Okay. Now later on in our discussion, we talk about how laser is generated and what should be the property of laser pulse. Okay. And okay. Coming back to this, the basic principle that we have already discussed, how the range is estimated. Then we had discussion on different types of LiDAR systems. Okay. So as I discussed before in the previous lecture, we have mainly two types of operation. If we say the first one is static operation and the second one is operation through the moving platform. Like in this case, when we talk this terrestrial laser scanner. Okay. So this is a 3D laser scanner. We'll discuss separately the difference between 3D and 2D LiDAR systems. 3D laser scanner means two angles are recorded. Like in the previous case, we discussed alpha and beta, where alpha is angle from the vertical z-axis, while beta is angle from a reference axis that is in horizontal plane. Okay. So it's a 3D laser scanner. It is mounted on a tripod, and this tripod is static platform. It is not moving. Okay. So except this terrestrial laser scanner, all other this LiDAR based operations, they are from dynamic platform. They are from moving platform. Like whether it is aircraft based, UAV, then this the vehicle that is operated through railway track or on through highways or roads. Okay. So on the basis of type of laser pulse, laser beam that we use, and on the basis of type of laser scanner, whether operation is 3D, 3-dimension or 2-dimension, we have derived criteria to classify the LiDAR systems. Okay. So the first one, if you see, the classification can be done on the basis of platform, while we can also do the classification on the basis of the basic unit, that is laser scanner. That basic unit operation is in 2D or 3D, and type of laser beam that we use. So type of laser beam, as I discussed before, we have pulse laser and continuous wave laser. So pulse laser, one laser pulse is generated, then no energy is further generated. Then after certain interval, next laser pulse is generated. Then we have, as I discussed before, using a electronic circuit or laser in a using a particular laser source, we can't generate a square laser pulse. It is not possible. So we generate a laser pulse where we have a certain rise time and fall time. We can't say the rise time is equal to 0 and fall time is equal to 0. Okay. If you remember, like in the previous slide, we discussed about how to characterize a laser pulse. Okay. So let's say this is time, this is amplitude. Okay. And that is a peak amplitude. We call it, let's say, AP. That is 100%. Okay. So at 50% level, we draw a line. Okay. Now let's see if we define it, the function ft that is equal to a. Okay. For 0 less than t less than or equal to t1. So let's say this is time t1, 0, and this is t1. So this is where to define the function ft that is equal to a. Obviously, it will be some function will be there because it is Gaussian. So a is not constant. Okay, this is variable, but we see the variation from 0 to t1. Okay, now further we define ft. What is the value of ft at we can say this 50% of AP. 50% of AP, that is equal to AP by 2. So you will get two values. Okay, one over here, another over there. So we can say it is A1 comma A2. So between these two, we have a range of we have a time difference, and it is a period of time. So we call it pulse with TP. That is very crucial parameter, this pulse with TP. Okay, so you need to remember how to characterize a laser pulse. Okay, because this will be further this will be discussed, like how it is associated to the accuracy of point coordinate measurement. There will further we in our discussion we consider these concepts. Okay, how to define a laser pulse as we are discussing over here. So at 50% level, that is AP by 2, we have A1 and A2. So between A1 and A2, this time is called TP. Okay, and 10% to 50%. Sorry, this is 90%. So it's you can 0.9 AP and this is 0.1 AP. So this is called as rise time. So we can't say this rise time TR is equal to 0. It is not possible using the any electronic circuit. So we have a specific rise time. This is the reason why we can't generate a square pulse. So we have a Gaussian, we have a laser pulse with Gaussian shape, near Gaussian shape. Then there is a gap, second pulse is generated like that. Okay. This is A and time T. And the second type of laser beam is that is continuous wave laser. Okay, so using continuous wave laser, like in this case, how we calculate the range? Range we calculated using C into time, that is calculated time of flight divided by 2. Okay, so it is this analysis we do on the basis of time difference between the time difference that measure the time between the time at what the laser beam is transmitted and the time at which laser beam is received at the receiver. While in case of continuous wave laser, where the variation is sinusoid or cosinusoid, we calculate the range on the basis of phase difference. So phase difference between transmitted laser pulse and received laser pulse. Okay, we'll see this mathematics. We'll see the analysis in detail using the mathematical concepts. So this is for the general understanding. Like in the first case, we do the calculation of range on the basis of time difference, while in second case, we do the calculation of range measurement by phase difference between transmitted and received laser pulse. That is laser beam. Okay. So this is also basis to categorize the LiDAR systems. Okay. And further, we have discussed about the detail of the objects which are acquired by various types of laser scanning systems. Okay. And as we have seen that at a different data point density, okay, the point coordinate or point clouds are acquired in different LiDAR systems. Okay, there is one query. Like if you see in this case, when the let me add one new slide over here. Or 3D laser scanner is mounted on tripod. Okay. Somewhere here we have a laser transmitter, center of laser transmitter. Okay. To this first laser pulse is transmitted. Okay. And let's say there is a surface on which this laser pulse is striking. So this is point 1 at which it strikes. Okay. And it is happened. First laser pulse, second laser pulse, third. Goes on. Okay. Now what happened? When this laser pulse is transmitted, there is a certain time gap. Okay. To this time gap, by the internal mechanism, the optics, this laser source optics, you can say, through which this laser beam is transmitted, it is oriented to some other direction. So there is some internal orientation. So within this given time, okay, we call it angular rotation. Okay. It is oriented and let's say by angle theta. So this theta is constant throughout. Second target point, there is the same time difference because this is periodic laser beam. Same time difference, it is again oriented, and obviously this angle will be same. So this is third. Okay. So meaning of density over here, like how closely these points are located. If they, so if we have a high point density, it means gap between 1 and 2, 2 and 3, what it will be? If we say the point density, to understand, okay, let me finish first. Yes. Just see over here, there are many points from the surface. Okay. So, so they represent the surface geometry. Okay. So point density means like there are many points on the surface. So density generally we define in 3 different way. If we are considering the surface, 2D surface, then we call it area density. Okay. When we are considering a 3-dimension, like this volumetric object or volumetric detail, then we call it volume density. Okay. When we are considering a line, something, some distribution along the line, then we call it line density. Fine. So in this case, let's say I'm considering a line density, because I'm considering the point just they are, though they are not along a line, but if we project it on the line, okay. So here I'm talking about line density. Okay. How many points we have per unit length of line? That is a line density. Similarly, in this case, we can, if you project all the point on 2D surface, then it will be area density. Then if you consider total volume in 3D, then it will become the volume density. Okay. So if these points are closely packed, it means the distance between two successive points, we can say, like 1 and 2 over here. Okay. If you reduce the gap, how this gap can be reduced? What are the ways? Then I will correlate why using different types of platform we get a different point density. Why they're not? Why the point densities are not same? Though in the coming lectures we'll have a detailed discussion on that. But though I'm mentioning differences in point density in the data acquired by the various through the various LiDAR operations. So a brief analysis is required over here. So this gap depends on how many parameters over here. Yeah, please, some of you we are responding.
Sir, angle.
Yes.
Sir,
Theta
and surface.
Yeah, theta, correct. This theta is one of the parameter. Okay, what else? That is correct. This angular separation between these two directions, that is angle theta. If you shift this surface, what will happen? At the same angle theta, now the spacing between these 2 points will reduce.
Yes, sir.
Am I correct? If you further shift, okay, again what will happen? Spacing reduce. So it also depends on the distance from laser source to target. So the point density that also define a quality of data depends on this theta as well as the distance, or you can say the range, as I'm discussing here. Okay. So now you have a general understanding. The point density that we obtain in the LiDAR point cloud data from the surface depends on the theta, that is angle between two successive fired laser pulses or laser beam, and distance from laser source to target. Okay. Now the mentioned time, this point density, here I am talking about area density, can be justified. Like if you see, in both cases, when the LiDAR system is operated through the ground-based platform, that is a moving vehicle through road or highways or through railway track, we can obtain 700 to 1000 points per meter square. Okay. So in this case, this operation is through the moving platform. Okay. And if we take another ground-based LiDAR system, that is TLS, So first we are considering the ground-based systems. So we have mobile LiDAR system that is operated through road or rail, and we have a LiDAR system operated through the tripod. TLS is acronym that is for terrestrial laser scanner. In this case, we have a point density more than this. A reason is that here we use 3D laser scanner. In this case, we use 2D laser scanner. You'll see the difference later on. Okay, so 2D laser scanner and 3D laser scanner. In this case, in both the cases, we can say the distance from laser source to target is nearly same. Okay, but you can see the difference in angle theta. That is angular spacing between two successive laser beams which are fired from the laser source. So theta will be less. We can say comparatively, the theta in vertical. See, we define two angles, alpha and beta. Though these two angles are different, these angles are from the vertical reference axis and horizontal reference axis. But when we see when two successive laser pulses are fired, okay, so the motion that is provided to fix a direction of laser beam is in vertical as well as horizontal direction both. I will take up this further in the, I think after 3 and 4 slides, we have discussion on this. So there will be more clarity, like why in case of TLS, that is where that we acquire the data using 3D laser scanner, we get a high point density compared to mobile laser scanning based data acquisition where we use 2D laser scanner. Yeah, because in 3D, we consider the two planes, vertical plane and horizontal plane both, where the laser beams are directed. While in case of 2D laser scanner, in one particular plane we fire the laser beam, and the third dimension we'll get when the platform itself moves. Okay, so we'll see it there. Then there will be more clarity along with that discussion. If we come to the airborne platform, okay, by maintaining the theta constant, the theta is a unit that gives you the angular separation between two fired laser beams. Okay, so theta constant, but you will get less point density because in this case we are using aerial platform. And in that case, the distance from laser source to target is more compared to the ground-based operation. Okay, so that parameter govern over here. That is the range from laser source to target, various target points. That is more. Okay. Now the least point density will get in airborne laser scanning, where the LiDAR system is operated. The entire system is operated through aircraft or plane. Okay. So in that case, we do the operation at the altitude of, let's say, 800 meter or 1 kilometer. 1 kilometer. So in this case, the distance between target points and laser source is highest among all types of laser scanning operation. So this is the reason why we get the least point density in case of airborne LiDAR. But this is the fastest scanning method to collect the data. Okay, so in very less time, we acquire a large area, and this is the fastest method among all. Now we'll see some of the highlights from the advantage side. So using LiDAR, if we compare it with other remote sensing techniques, so these advantages are highlighted mainly in the context of airborne LiDAR. Okay. So airborne laser scanning. Okay. So generalized systems, the LiDAR systems which are used in airborne laser scanning, using them, some values are highlighted over here. Like in LiDAR will get high accuracy. See, when we talk about point coordinate generation, okay, so there we define two types of accuracy. The vertical accuracy, that is in Z. We are calculating X, Y, and Z, where XY is the location from where that point is. And we have already discussed in the context of images. So in the images, we have only XY location of the pixels. In case of LiDAR, we have a third dimension as well. That is the depth of that point. So Z value we also calculate. So one accuracy we define, that is EA. It is a vertical accuracy that is along Z. And the horizontal accuracy we define what is a point that is in horizontal plane. Okay, what is the XY accuracy? How accurately we are locating a point in X and Y. So this using a general LiDAR instrument in ALS, nowadays we get better accuracy than this. So it's the horizontal accuracy is 20 to 30 centimeter, while the vertical accuracy is better. It's 5 to 15 centimeter. And it is high compared to the 3D point cloud generated through the stereo images. Data acquisition is very fast along with the processing. So using airborne LiDAR operation, the data collection can be done at any time of the day. Reason is that this LiDAR is active remote sensing technique or passive remote sensing technique?
Active remote sensing.
Alok Kumar, could you please unmute?
Yes, sir.
Yeah, Alok, tell me where this is the active remote sensing technique or passive?
So it is a active remote sensing technique because it
Okay.
have their own radiations are in form of laser.
Yeah, good. So this LiDAR is an active remote sensing technique. Reason is that LiDAR has its own internal energy source. So there is a laser source that generates its own laser beam, and it is integrated with the system itself. So this is the reason why we call it active remote sensing technique. And it can be done at any time of the day. Could you justify it? Why this statement is correct? Any one of you?
Sir, question, please pardon.
Our question is that how you can justify this statement? Data collection using LiDAR can be done at any time of the day, whether irrespective of day or night.
So because of it is active remote sensing technique, na? It does not require sir sun as a energy source.
Yeah, good, correct. So this LiDAR based operation is independent on the illumination that is generated by the sun. Okay, so its operation is independent on whether the time is day or night. Okay, so the LiDAR based data acquisition can be done even in night. Okay, so data collection can be done at any time of the day. If you see the data acquisition time, then for the general understanding, the 1000 square kilometer data can be acquired in only 12 hours. 1000 square kilometer is very large area. but data acquisition can be done in 12 hours. Okay. Now, one of the application using LiDAR is generation of digital elevation model, DEM. Okay. So further in data processing, after the data acquisition, in 12 hours, digital elevation model can be generated for this entire area, 1000 square kilometer. Okay. Now the third advantage of LiDAR is minimal human dependence. Okay. As I said before, once you initialize the instrument LiDAR system, it will automatically collect the data. Okay. And this is a direct georeferencing technique. I will explain it. What do you mean by direct georeferencing techniques? So further for the data refinement, we can say the data processing, we require very few ground control point or ground truth to correct the accuracy in the acquired data. So very accurate data is already required. And once you initialize the instrument, automatically it fires the laser beam, hit the ground point, hit the target point, and further processing is done to calculate the point coordinate. And further, in some cases, the refinement is required in terms of just analyzing how accurately a point coordinate is calculated. But for those cases, only few ground control points are required. And that is only for the check. Okay. So in that case, for generating a point coordinate, we don't require much ground control point. Okay. And the fourth one is data density. So I have already explained three different types of data density, that is line density, area, and volume. So just see the data rate at which the laser pulses are fired. In 1 second, the data rate is 900 kilohertz. So 90 lakh points per second, they are fired. Okay. And in case of airborne, 40 points per square meter. If data density rate is very fast, we can get point density, let's say up to 40 points per meter square. That can be obtained using airborne laser scanning. Though in this case, I have mentioned very few points, that is 4 to 15. But this point density, this area density can even goes higher, till 40 points per meter square, by implementing some modification in the instrument or this LiDAR system. If you increase the pulse firing rate, then 40 points per meter square can be obtained. These are the additional parameters on which point density depend. The important point is this multiple return to collect the 3D data. Okay. This is a special property of LiDAR based operation. Okay. The waveform capture and multiple return. I add over here a blank slide to discuss. What do we mean by multiple return? Okay, and why it is important? Let's say if we consider a forested area. So just this is a rough sketch that represents a tree. Okay, and let's say using an airborne LiDAR system, a laser beam is laser pulse is fired, and it is confined between these within this conical confinement. I will further explain why I am mentioning conical, not cylindrical. Within this conical confinement, let's say within this is the virtual shape of energy that is transmitted from the laser source. Okay. This energy travels within the conical confinement. Okay. And this energy pulse, that is energy of the pulse. It is fired from the laser transmitter, and this energy travels through this conical confinement. What happens over here? It interacts along the tree at multiple points. As you see in this case, this if you see this conical confinement, as I talked, this diameter is very less. Okay. And this laser beam find enough gaps within the canopy to propagate towards ground. Like if you see in this case, so this is a light source. Okay. So this light energy finds enough gap within the canopy to penetrate and goes deeper toward the ground. What happened? Let's say this is at our first interaction takes place. Then let's say somewhere here, the next interaction takes place. Then further third interaction takes place. And finally, it hit the ground. Okay. So what happens? If I draw over here the shape of laser pulse, it is like this. This is time t. And this is amplitude. Okay. Now, I will further explain how to calculate the energy within this laser pulse. Okay. Some energy, part of energy that is within this laser pulse, and it is traveling through this conical confinement. Okay, this is reflected back from here. So one return we get from here. Second return we get from here. Third return we'll get from here. Last return we get from the ground. So what happened? One return we get from here. Second over here. Third return. And final return. Okay. So if we plot, what will be the same of return? Like we'll talk about, no? So as previously we have discussed about, let's say this is a transmitted laser pulse. Okay, corresponding to this laser pulse, if it goes through the canopy, as in this case, what we have, let's say it happens at time t1. It is transmitted at time t1. So I can say this is time t1. Okay. In time advancement at t2, we have the first return. Now at t3, we have the second return. At t4, we have the third return. Okay. Finally, at t4, we have the last return. Okay. Now this will be the shape that will be further sensed at the receiver. So just see over here. In this case, we have only one peak, while in this case, we have a local maxima. We have 4 local maxima over here. Okay. And they are identified at the receiver. And we call it multiple returns. For one transmitted laser pulse, when it goes through the canopy, we get a multiple return. What does this mean? We have a coordinate of this point P1. Further, we have coordinate of point P2, point P3, and final P ground. Okay. Now we can you can distinguish, or you can differentiate the data which we collect using photogrammetry or imaging system and data we are getting through LiDAR for the forested area. What happens when you use aerial imaging? So what happens in aerial imaging? This is the camera. Okay. This is its field of view. When you click the image, you will only get pixels of the surface, outer surface. You don't get information of all these areas in photograph or in images. Okay. While in case of LiDAR, just you see, you are calculating the coordinate of this point, which is within the canopy, that is hidden within this exterior, outer exterior of the tree. Okay. Even you are getting a point coordinate of this, and this pulse is finally reaches to the ground. So you are getting information about the ground terrain as well. While in dense forest, you can't get pixels from the ground. Why it is so? Because the canopy is obstructing. This area is not open. Okay, so this tree canopy is obstructing these ground surfaces, which are just below the tree canopy. While in case of LiDAR, it's an active remote sensing technique. It can penetrate to the tree canopies. Okay, within this confinement, and it interact with the multiple locations, and finally it hit the ground. And what we do in digital elevation model, I hope the concept of DEM you are aware about. So digital elevation model is the information about the ground surfaces only. If let's say someone asks you to generate a DEM, so what you need to do? First, you need to remove this tree. Okay. Now this surface is DEM, digital elevation model. So DEM represent this surface. This is called as DEM. Okay. So which technique is better to generate DEM of the forested area? This image based or LiDAR based point cloud?
Sir, image based.
LiDAR
Sir,
based.
LiDAR based, sir.
LiDAR based.
Correct. It's a LiDAR based point cloud. Why it is so? Because in LiDAR you are getting a coordinate of ground surface points. While in case of images, you are only getting this information. You do, when you don't have a data of ground surface, how you can generate a DEM? You can't. Okay. Fine. So waveform capture. Waveform capture means the recording of this return. So this entire, the way at a different interaction point, the way transmitted pulse is reflected, this entire waveform is recorded. This will further help you in the forestry applications. So that I'm not discussing over here. This is a application part. So it will be seen in data processing. But this will be required. This will be a kind of added advantage for the forestry related applications. Like if your sensor is collecting the entire waveform shape, okay, if it is capturing the waveform, return waveform, then it will further help for the forest related studies or even the bathymetry related studies. Okay. Fine. Then next, the weather and light independence. So obviously it's a active remote sensing technique, so it does not require an external energy source like in case of satellite based imaging. It is also weather independent, but you can't do laser scanning in rainy season. One more point I would like to include over here. As we have discussed this one, if you see, what should be the property of laser that is generated by laser source? So one point, that is highly monochromatic. Highly monochromatic means this is the laser pulse, time t, this is amplitude. Okay. So this laser pulse is a combination of multiple photons. Obviously, when multiple photons are combined together, this shape is generated and you can able to calculate energy within the shape. So energy is composition of many photons which are comprising this shape. Now, when we talk about multiple photons are combined together, at what wavelength the photons are generated? So that is highly monochromatic. It means at a particular wavelength, fixed wavelength laser beam is generated. Okay, and generally for the LiDAR based operation, we keep this wavelength lambda in NIR band. Okay, and we call it eye-safe laser. Eye-safe class 4 laser. We'll have detailed discussion on this. So when this wavelength we choose in NIR band, okay, and now I'm saying over here, we avoid to perform laser scanning in rainy season. Can any one of you justify it? Like why we do not perform laser scanning in rainy season? I have already discussed the enough background to respond this query. Sunil, can you try to respond this query?
Yes, sir.
Yeah, please.
तो जो सर लेजर से जो लेजर निकलती है वो सर जो अगर रेनी सीजन में हम करेंगे तो जो वाटर की जो सर छोटी मतलब
हाँ, वाटर लॉग जो होगा, करेक्ट,
उसे सर स्ट्राइक करके सर आ जाएगी, तो हमें प्रॉपर इंफॉर्मेशन नहीं मिल पाएगी।
नहीं, जैसे मान लो ये है कि रेनी सीजन में हम लेजर स्कैनिंग करते हैं, ऑब्वियसली विल हैव अ लॉट ऑफ वाटर लॉग। ओके, तो हर जगह पे क्या होगा, या तो वेट सरफेस होगा या पानी लगा होगा वहां पे, ठीक है।
यस सर।
तो यदि मान लो वेट सरफेस होगा या वाटर कंटेंट, हर एक टारगेट पॉइंट पे वाटर कंटेंट होगा, ठीक है, तो उससे क्या दिक्कत हो सकती है? कंसीडर दिस पॉइंट इन माइंड, जो द वेवलेंथ एट विच वी आर जनरेटिंग द लेजर बीम is selected in NIR band and it is class 4. Yes. If you see the spectral signature of water, clear water, so what it is, less than 20%, this is wavelength and this is a reflectance. Okay. So we get reflectance only in visible spectrum, is it? While in clear water NIR band में what we get a reflectance, it is 0, and I think
0.
this is less than 20% even. Even in the visual spectrum, we have a reflectance less than 20%. And if you move forward along the higher side on the wavelength axis, it is 0 after visual spectrum. So what happens when there is a water content on the target point? So due to the low reflectance of water in NIR band, what will happen? The amplitude of return, this will further decrease because this amplitude is due to the reflection from the surface. No? If this target is interacting P1, it is reflected back at P2, again reflected, P3 reflected. So what will happen? From the ground or even from the tree leaves, there will be water content in the rainy season. So the water content will be responsible for decrease in amplitude of the return. I talk about the local maxima. So amplitude, this local maxima value will further decrease. And it will decrease to a level that the receiver can't identify due to its internal sensitivity. Okay. So though in general weather, we can do the remote sensing, but in heavy rainy season, if there is a heavy rain outside and significant water is there on the target points or surfaces, we avoid to go with laser scanning. Okay, now digital compatibility. So this is a direct georeferencing technique. It means if I consider this point, in the previous case, all these points, their coordinates are in a WGS84. Okay, they are georeferenced. So they are directly compatible with the GIS databases, which are already there in global coordinate system and in WGS84. So no need to convert a point coordinate further into the globally defined coordinate system. Okay, so you can directly import. Like if you want to if you want to draw a particular trajectory on Google Earth, what do? You have a certain set of points and you generate a KML file and you import within the Google Earth and you can see a line. So what is the requirement? To just match the drawn line to the actual location, that the data set from which you have generated a KML file, that coordinate system should be same as coordinate system used by the Google Earth, that is WGS84. In LiDAR point cloud, you can directly import, and that will just you can see at the right location. That will represent the object within the Google Earth that is represented in 2D. Okay, like let's say from the LiDAR point cloud data, if you extract the road, okay, so that road is already in WGS84 coordinate system, the road points. And if you generate a KML file and if you import it within the Google Earth, it will exactly match with the road pixels which are there in the Google Earth imagery. This is the meaning of data digital compatibility. There is no need to transform that point coordinate because that is already there in global coordinate system. So this can be directly, this point cloud points coordinate that is collected by the LiDAR can be directly combined with other data types. You can combine it with the imagery, because in the imagery this XY coordinate of pixel is given in global coordinate system. Okay. Next, we have a bathymetric observations. Bathymetric observations means underwater study, underwater surface generation up to a certain depth can be done using LiDAR. That is can't be performed using image-based operation. and we'll see it. Bathymetric observation. Bathymetric means it is related to the water related study. Now canopy penetration, that we have already discussed. We call it canopy penetration. Okay, and it is already shown over here. This one. The laser beam finds enough gap through the canopy to travel along its length, and finally it is strike to the ground, and we have a multiple returns as you see in this figure. So there are many local maxima. Okay, an entire shape of return waveform is captured as well. Now let me know if you have any query related to these basic concepts, because we are just discussing the background and general understanding of LiDAR. And simultaneously, we have been highlighting its advantages over other techniques like satellite imaging and photogrammetry.
Hello, sir.
Yeah, Shivam, बताओ.
सर जब जब सर डाटा कलेक्ट करने के बाद इसको सर स्टैटिक के पॉइंट से अलाइन करना पड़ता है.
नहीं, could you further explain it, like what you are talking about? We have हाँ बताओ.
सर जैसे डीजीपीएस में सर 2 इंस्ट्रूमेंट सर एक साथ वर्क करते हैं. टू डीजीपीएस की 1 करेक्शन देता है और एक को सर डाटा कलेक्ट करते हैं एक से. ऐसे ही सर इसमें भी कोई 2 इंस्ट्रूमेंट होते हैं या सिंगली वर्क करता है सर, या बाद में हम स्टैटिक से मैच कराते हैं इसका डाटा कोई स्टैटिक पॉइंट से.
Okay, I got your point. Okay, see, like in GNSS, to improve the accuracy of data collected, like that is computation of a point coordinate, we use a concept of base and rover. Okay, so we use a base platform to apply the correction to improve the accuracy of point coordinate. Fine. In this case, we don't use such kind of post processing. Though if you see the LiDAR system, then in LiDAR system, we have a laser scanner unit. Along with the laser scanner unit, we have a GNSS as well. Though the complete operation I have not discussed it, but GNSS is a part of LiDAR system, and the laser scanner is the basic unit. So GNSS is used for generating a point coordinate in a WGS84. Okay, so to improve the GNSS measurement, in this case as well, we use base and rover both. So whatever you have, you perform for calculating a point coordinate using GNSS, the same operation is included in the LiDAR, because the GNSS based point coordinate computation is one of the steps in LiDAR, along with the raw information that is recorded by laser scanner unit, that is range, alpha and beta, 2 angles and 1 range. So, but as I discussed over here, ground control point, like in imagery, we apply corrections in the imagery. In this course, you will learn about geometric and radiometric corrections we apply in images to improve its quality. such kind of corrections we generally don't require in LiDAR measurement. Whatever we get, whatever the point coordinate that is recorded, that can be directly used for the various applications. Okay, now one by one we'll see the advantages of LiDAR and we'll discuss them in detail. So the first one is the using the capability of canopy penetration. So as you see in the figure, uh, in airborne laser scanning, once the laser beam is fired, it can travel through the canopy and goes to the ground. Okay. So we can say that it can see beneath through the canopy so that the enough ground points are acquired. Just see over here, the green color represents the trees which are over the ground surface and the water canal is passing through that. Okay. And these are the ground surfaces. So there are many ground points. Through the canopy, laser beam goes through, okay, and finally hit the ground. So we can able to generate a digital elevation model in the forested area as well. Unlike photogrammetry, in photogrammetry or satellite imagery, we cannot able to generate accurate DEM from the dense forested area. Reason is that we can't get the pixel information from the ground surfaces beneath the canopy. Okay. Now we will highlight the various application domain of LiDAR. Okay. So we have already seen the LiDAR is very fast, accurate, and it can provide comprehensive and detailed information compared to other remote sensing techniques. Okay. And we have many areas where nowadays the LiDAR system is being used, like project planning and development. If we see, then for the topographic mapping, roadway analysis, we use mobile LiDAR, environmental studies, roadway analysis and measurement. If we come to the construction industry, then for the quantity and as built and repaired related applications, okay, and the documentation related to them, machine control and construction automation. In construction automation industry as well, we use LiDAR as a tool for the information generation. Then when we come to the maintenance related application areas, then drainage, flooding, vegetation, bridge information modeling, power line corridor mapping, and related applications, we use nowadays we are using the LiDAR. Okay, and it is preferred over other remote sensing techniques due to these three advantages. Then various operations like land use and zoning, traffic parking, building information model, bridge information model, emergency responses. Similarly, in tourism and safety and research related applications, asset management. So we have a lot of application areas where LiDAR technique is playing a significant role nowadays. Okay, if we talk about floods, then digital elevation model is one of the important information that we need to have in case of flooding. Because using DEM, you can have information about low-lying areas. Okay, and we can generate very accurate DEM using LiDAR. So for the floods related application, improving the flood forecast models and flood hazard zoning operations, LiDAR-based data helps. Then further determination of friction coefficient on floodplains, topographic data that is having information about flooding zone, flooded area, and input to the GIS-based relief, rescue, and flood simulation operations. So LiDAR derived data product will be taken as an input for these simulation operations. Okay, so LiDAR is acting as a very important tool to generate data sets which are required, okay, for the flood related management. Then we use the LiDAR for coastal applications in coastal engineering, flood management, erosion monitoring. How it can be done? By using a LiDAR, you can able to generate an actual mathematical surface. If let's say erosion takes place during certain period of time, then again you do the LiDAR mapping and you generate a mathematical surface at that time. So at two different epoch, you have a mathematical surface, okay, of the given area. And by differentiating, by comparing the mathematical surface, you can analyze the volume of erosion takes place due course of time. Okay, and similarly, due to this, we also have its application in mining. In mining also, we work in the same line. First, the area where you want to do the excavation work, mining related excavation work, before the activity, do the laser scanning, generate a 3D surface. Once task is done, again excavation work is done, again do the laser scanning and generate a mathematical surface. When you differentiate two mathematical surfaces, and that is 3D surfaces, because in LiDAR we have a Z, we have a depth of the point. When you generate a mathematical surfaces, you differentiate them, you will get a total volume of material that has been excavated. Like if you see in this case, in the first slide, I think in the starting, this slide, sixth slide, when you fire the laser pulses, what information you are getting? You are getting a 3D point coordinate. Okay. And if you interpolate all these points, you will get a mathematical surface of this area. Okay. Let's say somewhere this before the excavation, okay, you do the laser scanning, and after the excavation, you do the laser scanning. So what you will get a two different mathematical surface, and if you differentiate them, then you will get a total amount, total volume of material that has been excavated. So this can only be done using LiDAR, because in LiDAR you have a 2D geometric information as well as depth of the point. So you can able to generate a 3D mathematical surface. Now we use LiDAR for bathymetric applications. Okay, in this case, what happens? As we discussed before, when we generate a laser in NIR band. Okay, so in NIR band, it can't be reflected from the water as it is absorbed by the water. So for the water body related application, for bathymetric application, we generate laser beam at two different wavelength. Okay, lambda 1 and lambda 2. So lambda 1, it's lower wavelength, it's a green laser. And while in lambda 2, it is selected in NIR, which is shown over here in red color. So green laser is generated in a visible spectrum, though it is not eye safe, but though we are using it for the water related applications. So and the lambda-2, that is and the second laser beam that is generated in NIR band. So the green laser can goes to the water. Okay, it hit the ground, it hit the water bed. So we'll get a two reflection. First one from the water surface and the second one from the water bed. So let's say if a plot over here the laser pulse, that is time t and amplitude. It is a laser pulse generated in as a green laser. Okay, so this laser pulse is transmitted over here. Okay. Then the first interaction takes place at the water surface. First interaction takes place at the water surface, and we have a reflected laser from here. And the second, when it goes inside the water bed, we have a second reflection from here. So corresponding to one transmitted laser pulse, we have a two return. And if you see, if we consider it, the laser beam is hitting along the vertical, though it is shown slant over here, but let's say for the general understanding, so this depth of the water can be estimated using the time difference information between these two. Okay, we'll see it in detail later on. So for the river and coastal navigation channels mapping, we use LiDAR. And further for river and coastal bed topography, so these are the various bathymetric related applications where we use LiDAR, and these are the basic, this is the basic principle through which LiDAR systems operate for the geometrical information acquisition from the water surface as well as from the water bed. So do you have any query related to the discussion we had?